As one moves from the equator towards the poles, steadily decreasing temperatures are observed. In the same way, there is a steady decrease of temperature with increasing elevation in the atmosphere. This decrease of temperature with increasing altitudes in the atmosphere is called the vertical temperature gradient. After going through this module, you will be able to understand horizontal distribution of temperature, annual temperature range, seasonal distribution of temperature. Vertical temperature gradients are partly controlled by energy transfers and partly by the vertical motion in the air. However, various factors affecting the vertical temperature gradients interact in complex manner. Energy transfers involve the latent heat of condensation, cooling of air by the process of radiation, and sensible heat transfer from the ground. Vertical motion is closely related to the pressure systems. High pressure systems produce descending air currents which lead to warming of extensive layers of the air. This results in the decrease of vertical temperature gradient. On the other hand, low pressure systems give rise to ascending air currents which cool by expansion. This increase in the vertical temperature gradient. Moisture is said to be an additional factor which creates a lot of complications in the vertical distribution of temperature. The observed rate of vertical decrease in the temperature, also called vertical temperature gradient, is called the lapse rate. Lapse rate is not constant but varies with height, location or season. The lapse rate at a given place and time can be obtained only by actual observations. It should be noted that the lapse rate indicates the temperature conditions that are found in a stationary column of air, characterized by the absence of any vertical motion. The upward decrease in temperature of the air continues only up to the base of tropopause, beyond which it stops. In the lower layers of the tropopause, the lapse rate may be very high on clear sunny days. On occasions, the rate of decrease of temperature may even exceed the adiabatic rate. In the tropical regions where insolation is very intense, the lapse rate is generally super adiabatic up to 160 meters on most afternoons, especially in dry summer season. Contrary to it, clear and calm nights during winter characterized by rapid nocturnal cooling produce a vertical temperature gradient that may be less than the adiabatic. A diagrammatic representation of different patterns of the lapse rate, also called the actual lapse rate or the environmental lapse rate, has been given. Lapse rates may be low or steep depending on the atmospheric conditions. Of course, the actual lapse rate in a particular place may be entirely different at different times. The fact that the temperature in the lower layers of the troposphere shows an upward decrease goes to prove that the direct source of atmospheric heat lies at the Earth's surface. Thus, as the distance from the direct source of energy, that is the Earth's surface, increases, the air naturally becomes progressively cooler, though only up to a certain height. It is noteworthy that heating of the lower layers of air is not caused because of the nearness to the Earth's surface alone, but there are other factors as well. The air closer to the Earth's surface is denser than the upper air and contains a large quantity of water vapor, dust particles and water droplets. On the contrary, air in the upper strata of the atmosphere is rarefied, dry, and there are little dust particles. Therefore, because of the lesser amount of water vapor and carbon dioxide, the upper air does not absorb as much heat received from the terrestrial radiation as is done by the lower air. Besides, the upper air being more transparent to the incoming shortwave solar radiation, despite the intensity of solar rays, its temperature is always relatively lower. Even on mountain slopes exposed to the sun, there is a large difference in the temperature of ground and that of the free air. In the same way, on high plateaus, there is a large difference in the temperature taken in the shade and the sun. The conditions of atmosphere and the differences in elevations or local relief features also affect the vertical temperature gradient. If a valley in the mountainous region is filled with cold and dense air, or there is an advection of cold air in the upper part of the atmosphere, the vertical lapse rate is likely to become lower. There is a smaller vertical temperature gradient. If the layer of air near the surface gets colder because of its contact with the chilled surface of the earth. On the contrary, if the surface is intensely heated during daytime, the air lying close to it is also heated by the processes of heat transfer. Under these conditions, the lapse rate becomes steeper, as often occurs on most afternoons during the dry season. Thus, it is clear that sometimes the actual lapse rate is larger than the normal lapse rate, and at times it is smaller than that. In general, the actual lapse rate or the environmental lapse rate is always different from the normal lapse rate. It may also be noted that the temperature variation with altitude is many times greater than the latitudinal variation. Continents and oceans not only influence the horizontal distribution of temperature, but they also affect its vertical distribution. In summer, the vertical temperature gradient is steeper over the continents, while in winter it is steeper over the oceans. There are certain levels in the atmosphere where under certain conditions, the normal condition of a decrease in temperature with elevation is reversed, and temperatures increase with altitude on a temporary and local basis. Since in these conditions the cold air is overlaid by the warmer air, the normal lapse rate is reversed. That is why this phenomena is known as the temperature inversion. In winter in polar regions, the layers of air close to the surface become so cold that up to a certain height, the temperature increases with elevation. During the colder part of the year, surface inversion in that region is a common phenomenon. Outside the polar region, the inversion of temperature of the continents is of common occurrence during the winter. But on the oceans, inversion of temperature frequently occurs in summer. However, these inversions are confined only to the lower part of the troposphere. Austin Miller holds the view that the lapse rate is lower in winter than in summer. It is lower at the night than during the daytime. Similarly, the plateaus and the mountains exhibit varying lapse rates in the air above them. Air over the plateaus has definitely a lower lapse rate than that over the mountains. As an exception to this rule, in winter the lapse rate in eastern Brazil is 8.5 degrees Celsius per kilometer, while in summer it is only 3.7 degrees Celsius per kilometer. Another salient feature of this lapse rate is that in tropical regions, the decrease in temperature with elevation continues up to a height of 16 to 18 kilometers in the troposphere. In this zone, the temperature at the outer boundary of the troposphere is reduced to 80 degrees Celsius, but in the polar region, the lapse rate continues up to 6 kilometers only. In winter, this height is beyond further reduced. Beyond latitude 60 degree north and south, the height of tropopause is 10 kilometers in summer and 9 kilometers in winter. The height of tropopause in higher latitudes is relatively less. That is why the temperature in equatorial tropopause is less than that in the middle latitude regions. Thus, at the same height from the Earth's surface, temperatures in the stratosphere increases from equator to poleward. During the summer months, this increase in stratospheric temperature continues up to the poles. But in winter, the sun being invisible in the polar regions, the temperature begins to decrease beyond the latitude 60 degree north and south to the poles. In winter, the stratosphere is warmest between 50 degrees and 60 degrees latitudes. Besides latitude, continents and oceans also have influence on high stratospheric temperature. The fact that the lapse rate suddenly drops to zero at the outer boundary of the troposphere indicates that convectional currents rise up to this level only. The following are some of the most important features of vertical distribution of temperature. The normal lapse rate is uniform at all levels in the troposphere in all latitudes. The normal lapse rate abruptly drops to zero at the upper boundary of the tropopause. In the lower part of the stratosphere, temperature at all levels is the same and there is little change in it. In the stratosphere, the temperatures gradually increase from the equator towards the poles at each and every level. This is mainly due to the fact that stratosphere is lower at the poles. An accurate knowledge of the vertical distribution of temperature in different layers of the atmosphere is of great help in understanding the exchange of heat by radiation between the Earth's surface and the atmosphere. Therefore, for a correct appraisal of different weather processes going on in the atmosphere, a comprehensive knowledge of the vertical distribution of temperature as well as humidity, at least in the troposphere, becomes all the more necessary. In the lower part of the atmosphere, up to a height of 8 to 18 kilometers from the surface, temperature normally decreases with increasing altitude. The normal lapse rate, as stated earlier, is 6.5 degrees Celsius per kilometer. But sometimes under special circumstances, it is reversed and the temperature, instead of decreasing, is found to increase with elevation, though only in certain layers of the atmosphere. In other words, the vertical temperature gradient is inverted. Temperature inversion may occur at low levels close to the land surface, or it may also develop at various atmospheric levels at different altitudes from the Earth's surface. According to the processes that cause them and the relative heights from the Earth's surface at which they develop, the temperature inversions may be classified in the following types: ground or surface inversion, radiation inversion, advection inversion. Nextly, the upper air inversions, subsidence inversion, turbulence and convective inversions, or the frontal inversions. Radiation inversion. The surface inversion produced by radiational cooling of lower air is called radiational inversion. The inversion layer develops at an altitude of about 90 meters. Nocturnal cooling produced by the terrestrial radiation is the principal factor for this type of temperature inversion. Since a land surface radiates more heat than the air, ground cools more rapidly than the air at greater inversion heights during night time. Consequently, the coldest air lies at the ground and is overlaid by warmer air. The layers of air in close proximity of the Earth's surface are cooled by the process of radiation and conduction more quickly than the upper layers of the air. Thus, at a certain height, 90 meters, the temperature increases with altitude, and this increase continues up to about 300 meters from the surface. Temperature inversion near the surface may produce under the following circumstances: long and clear winter nights, clear skies or skies with high clouds, relatively dry air, calm air, and snow covered surface. In higher latitudes where the ground is snow covered, solar radiation falling on it is partly reflected back. Thus, the ground heats little by the day. On the other hand, at night there is unretarded loss of heat by the Earth's radiation. Moreover, snow being a conductor of heat, it retards the outgoing radiation from the surface lying hidden under it. Therefore, the air near the surface undergoes rapid cooling and a temperature inversion is fully developed. Advection inversion. Advection of thick layer of the warm air over a cold surface produces an inversion of temperature in the lower layers of the atmosphere, for the warm air is cooled by conduction. Of course, this type of inversion occurring at a certain height, that is, the height of warmer layer of the air, is called advection inversion. This type of stable inversion occurs when the warm air passes over a cold water surface. Under these conditions, it may also occur over cold land surface or snow covered ground. In the same way, during summer, the oceans are colder than the adjacent land masses. So, when a cool mass of air is transported to the land, the presence of warmer mass of air aloft produces the same type of advection inversion. Warm and moist air masses coming from the oceans produce stable inversion over the vast snow covered lowland of northern Eurasia and northern Canada. Because of the greater frequency of temperature inversions in cold months of the year, the lapse rates are low in winter and steep in summer. Subsidence inversion. Subsidence inversion, as the name indicates, is produced 20 degrees well above the Earth's surface on the account of subsidence of air currents. This type of upper air inversion occurs in an air mass 10 degrees Celsius per kilometer. In certain cases, the subsidence continues to a particular level where the air diverges horizontally over a lower layer. Temperature inversion of this type generally develops in a layer separating the upper region of subsiding air and the lower region, characterized by the absence of vertical motion. Subsidence inversions are of common occurrence in regions of higher pressure that are characterized by sinking air. There are circumstances which during the night, two inversion layers may develop in the high pressure regions. one at the ground produced by radiational cooling and the other at the considerable altitudes produced by subsidence. There are semi-permanent high pressure regions in the Atlantic and Pacific Oceans in the latitude of 30° north, which are called the Azores High and the Pacific High respectively. Subsidence in the eastern portions of these anticyclones being more pronounced leads to strong temperature inversions, usually about 500 meters to 1000 meters above the sea level. The subsidence inversion is of great environmental significance for the pollutants from motor vehicles and other industrial sources become concentrated in lower layers of the atmosphere and thus form a great environmental hazard to the inhabitants of the industrial towns. Trade wind inversion. Well-developed subsidence inversions are found over the lower trade winds. The thickness of the inversion layers varies from a few hundred to about 1000 meters and increases as the trade wind proceeds towards the lower latitudes. These upper air inversions of the trade winds are associated with the warm anticyclones of the tropical regions. The trade wind inversion layer has different values of temperatures in the upper and lower portions. The difference in the temperatures between the top and the bottom of the inversion layer may vary over the eastern parts of the subtropical anticyclones. Besides, the inversion is more pronounced during the winter than during summer. The trade wind inversion prevents the vertical air movements. This is why precipitation in the trade wind areas is only modest. However, when atmospheric disturbances destroy or lift the inversion layer, the precipitation may be fairly large. Near the intertropical convergence zone or equator, because of the prevailing convergence, the inversion layer gently disappears. Since upper air inversion of the type described above does not allow the upward movement of the heat and moisture originating from the surface, the upper trades are found to be dry and more stable. Atmospheric conditions above and below the inversional layer show a sharp contrast. Above the inversion layer, the lapse rate is steep, approaching dry the adiabatic rate, but the air is dry. On contrary, below the inversion, the vertical temperature gradient is steep. Moisture content of the air is high and there is a larger amount of cloudiness. Trade wind inversion plays a vital role in controlling the vertical circulation in the tropical atmosphere by restricting the vertical development of the clouds. It virtually acts as a lid which effectively limits convection. Turbulence and convective inversion. This type of inversion is produced at altitudes above the surface by mechanical processes. Turbulence and convection are the contributory factors in causing this type of inversion. Because of the frictional forces, eddies form in the lower layers of the atmosphere which transport lower air to higher levels and bring back the upper air to the lower levels. Convectional currents set up in the air near the ground are merely responsible for the exchange of air between upper and lower levels of the atmosphere. The phenomena of turbulence and convection cause thorough mixing of the atmosphere in the turbulent layers. However, the turbulent or convective mixing is limited to a certain height beyond which it does not and cannot penetrate. It is at this height that the convective inversion is formed. In the process of vertical mixing, the air carried upward is cooled adiabatically. Similarly, the air brought downward is heated at the same adiabatic rate. After a prolonged mixing in the atmosphere, the air at the maximum height of the turbulent penetration becomes colder than what it was before, and that at the bottom of the turbulence layer will be warmer than what it originally was. This transition from the cold upper part of the turbulence zone to the air above with its temperature unaffected by the adiabatic cooling comprises a temperature inversion. Clouds, if they ever form in this inversion layer, are of stratus or stratocumulus type. In certain situations, turbulence in association with the heat from the ground leads to the formation of cumulus or cumulonimbus clouds. Turbulence inversion may occur at a low level or it may form at a very high altitudes. In case the inversion has formed at lower levels, smoke, dust particles and other pollutants are carried up to the inversion where they spread beneath the inversion layer and form distinct smoke or haze lines in clear weather. On the other hand, the anvil shaped upper portion of cumulonimbus clouds is result of an inversion at considerable heights. It may be interesting to note that stratiform clouds appearing in the sky are indicative of presence of an inversion layer above them. Sometimes the upper air inversion, by imposing a restriction on their vertical growth, makes the cumulus clouds stunted in the appearance. Frontal inversion. The inverted lapse rate at the front is called the frontal inversion. When differing air masses are brought together by converging movements, the warmer air, being relatively higher, tends to overlie the colder and denser air in a horizontal layer. However, because of the Coriolis force, the boundary zone between the air masses with the contrasting physical properties are never horizontal. They are rather sloping. In fact, the frontal zone itself is converted into inversion layer in which the lapse rate is inverted. In other words, at the frontal zone, as one moves up from the lower to the upper layers of the atmosphere, there is an increase in temperature with increasing altitudes. The following characteristics distinguish frontal inversion from other types of inversion. The inversion layer associated with the fronts is sloping, while in the other types of inversion, it is horizontal. In the frontal inversion, the moisture content shows a marked increase with elevation, while in other types the temperature increases and humidity decreases with increasing elevation. That is why the above inversion layer clouds are generally seen. In other words, the frontal inversions show an increasing specific humidity in the inversion layer. It is generally seen that along the fronts, the inversion, in the strictest sense of the term, it is never found. What happens is that actual lapse rate becomes very low in the inversion layer. The reason is quite simple. The warmer air masses ascend the retreating wedge of cold air and they cool by adiabatic expansion. Because of expansional cooling of the upward moving air at adiabatic rate, the frontal inversions are rarely observed beyond the height of 2 kilometers. At greater heights, there is a marked decrease in the lapse rate in the frontal zone, whereas just above the top of the clouds formed by rising warm air currents, the inversion is always present. Recent investigations attach special significance to frontal inversions in the origin of extratropical cyclones. To summarize this chapter, the vertical distribution of temperature, we have learnt about the normal lapse rate and the temperature inversion. Normal lapse rate is also defined as increasing height with decreasing temperature at a rate of 6 degrees